One of the obvious attributes of living systems is complexity. This is a term we have been using all over our lectures without trying to actually define properly in a quantitative way what complexity is. In this lecture, we're trying to do that, to provide a first idea, first theoretical approximation of how to deal with complexity, what might be the meaning, why emergence in complex systems is what drives actually the emergence and the appearance of all this complexity, and how life is connected to that, and also what kind of simple model can actually illustrate this idea. Well, let's first think about that, right? What is complexity, what is order, and what is disorder? It's easy to identify the limit cases, okay? What is an ordered system? Pues, for example, a crystal, like the ones we have, we don't see them because they are very small, but table salt crystals, they are cubic structures made of a completely regular arrangement of two types of atoms, right? Sodium and chloride, and as you know well, both of them are harmful, but the combination leads to a completely different kind of structure. A reminder that emergent phenomena are in multiple scales. However, the structure is extremely simple. Once I know that essentially I have a lattice where the atoms of each element are organized like this, right? I just need to know about a very tiny part and extrapolate. Everything else is exactly the same, right? Exactly the same structure. So it's easy to identify that there's a huge regularity here. The same happens with dynamical phenomena we can see in physics, like clocks, right? There's a completely repeatable pattern over time. If I go into the axis, this axis that I haven't yet defined, and I move from order to disorder, what kind of example would you give of disordered system? And clearly the most obvious one would be a gas, right? An ideal gas where molecules or atoms just move around a given volume, okay? Essentially disconnected with each other, and where the right description is just at the level of statistics. Okay, but what about in the middle, right? In our lectures, we've been talking about the things that populate this domain. And I'm making this just made up, this assumption that there's somehow a way of defining complexity, right? The complex nature of the structures we see in biology. Obviously, at least from our intuition, neither a gas or a crystal are complex, right? Once again, even for the gas, once I know the properties of a small fraction of the volume, I know everything, right? Statistically exactly the same. However, when we move here, right, what do we have, right? What kind of things we have? We observe things like cells, right? Cells reveal very well this compromise between order and disorder. You might see the cell, something that is very regular, that maintains itself over time, but it's actually a very highly dynamical system. And in particular, if you look inside in a eukaryotic cell, the microtubules that maintain the structure and allow the structure to change and keep organized is a highly dynamical system of waves of creation and destruction all over the place. We've been talking about the brain, right? And at some point we discussed the idea that brains actually seem to inhabit a critical point, a domain between order and disorder, and so on and so forth. What is in other places? What examples can I give? Let me just give you an example that's located, for example, here, right? To give a very different example, you look at Jupiter, the giant planet. You have this very complex turbulent atmosphere with an interesting object in the middle, right? It's called a red spot. Okay, where turbulence, one of the things that we still don't understand well in physics, turbulence dominates the behavior of the system, and we can identify a huge island of order resulting from nonlinear dynamics and interactions. That's the big point, interactions. What else could be there? Things that we have been discussing at some point. Here I could have living things like a tumor organoid, right? Something that is organized and is alive, but is more disorganized than a normal living system. We have organoids here, etc., etc. All right, the diagram I just plot here, right? You could ask yourself, why this shape? Why such a big peak here, right? So this is a compromise here between order and disorder that seems necessary. And that's one of the big points that I want to make in this lecture, that biological systems as complex adaptive systems require some part of order and some part of disorder. Order is relevant to have memory and stable processes, whereas disorder, in our case, implies the potential for disorganizing the system in a way and being able to adapt to different conditions. Right, if I go into something like molecular complexity, that's a particularly interesting case because here also we can identify well the extreme cases. Here again, I will have, as before, easy to obtain crystals from chemistry when I don't have big combinatorial thing at work. If I go into something like, let's say, a Miller experiment, right? When I put a mixture of simple components, I heat them, and all over the place we start to see large molecules being formed, but essentially it's not completely random. It's got quite random soup of things, right? Random polymers. Okay, and what is in the middle? In the middle, somewhere, and I want to make the point because it's important, we can have things that have an extraordinary complexity and result from evolutionary dynamics. And of course, DNA is at the top. Okay? In that respect, it's interesting to remember what physicist Erwin Schrödinger said about DNA when it was still not known what kind of information was pervading biological complexity. What was the origins of inheritance? At the time of Schrödinger in the 50s, there was the idea that maybe proteins are responsible for keeping information in cells and responsible for the inheritance. And Schrödinger made this very interesting conjecture in his little book, What is Life? Saying that whatever is there, and he was advocating for nucleic acids, it has to be something like an aperiodic crystal, right? A great intuition, because indeed, DNA is a very regular structure, right? But allows hyperestromic combinatorics, right? So that was really good intuition, and again, life somehow requires precisely combining regularity, even at the molecular level, and some amount of combinatorial flexibility. Okay, so again, that's fine, but if we want to plot these and connect these with real systems or model systems, we need to actually define, weight this axis, right? And in particular, having some measure of complexity that makes sense. What I'm going to define is kind of, for this freshman course, is kind of the minimal way of actually defining both things, right? Disorder in order and complexity. We'll keep going with that when we define the idea of entropy, but since we are not yet working on information theory, what I'm going to use is a surrogate of quantitative measures that can be really helpful. Let's start with a simple one, something that allows to define order and disorder, right, in an intuitive mathematical way. And to do that, let me consider the following. Imagine I have a system that is composed by a number of units that can have a number of states, right? To just have some starting idea, let's consider that my set of states for example, has to do with a collection of dice that, and dice that I can use, and they can have, as you know, 6 possible states, right? Okay, that could be also for coins, right? Heads and tails would be the other possibility, right? And I have a collection of n coins. No matter the example, the thing is, imagine I have my objects, right, on a table, and they can have a range of possible states. For example, I could have made up this, right? Having all my dice heading up with ones, just ones, right? All of them. Well, let's say this is the first, the last, okay? Okay, let me use, yeah, that's fine. That's clearly a completely homogeneous state, right? And as you know from your intuition, you have to create that state, right? So everything is exactly the same. There are many possible configurations, and one of them also is that all dice are completely random in their state, right? I've been shaking the table, for example, and I can see ones, I can see whatever is there, right? But the idea is that in this case, the probability of having a 1 is 1. Everyone is in that state. Whereas the probability of having a state different from 1 is 0. It's a completely homogeneous system. Everything is exactly the same, all right? In that case, the way of describing this is that the probability of having any of these states, right? And of course, this is k is 1, 6, okay? It's exactly the same for everyone. It's 1/6, right? Assume that you have a big collection of dice for all k. Right? Completely homogeneous state in the sense that every single possibility is being equally represented. Right? So this sounds a little like what I've been saying in intuitive terms. In this case, it's very easy to say something about the state of the system because everything is exactly the same. It's totally homogeneous, if you want. It's a very ordered state. Right? This one, we can actually create it by shaking the system, by pushing the system into complete disorder. And the result of that is that you have this homogeneous distribution. So our first intuition about measuring order and disorder is that it has to do somehow with how random, how homogeneously distributed are probabilities in that particular system. Okay? All right. Now, the thing is, having this in mind, and knowing that you have many possible intermediate states, how can I measure that, right? One of the measures I can use is called the Simpsons Index. Diversity it's called diversity or Simpsons Index. Okay? All right. So the definition goes as follows. We have the sum over states, S equals 6 in this case, square of probabilities. Why this index? Well, this index is functionally useful because it contains the basic idea I just was mentioning. It's an index that measures the degree of homogeneity of the system, right? In which way? Well, imagine I'm going to write down the two extreme cases, okay? Imagine a system like this where only one state is available, right? Suppose that I have this, okay? And the rest for k different of 1 or 2 or whatever, that's totally arbitrary, right? What would be the Simpsons index? Well, ds of this state 1, 0, 0 will be what? Right, we'll have 1. And only one of the probabilities here is a 1. The rest is 0. So it's 1 squared, 1 minus 1, 0. So for a system that is completely homogeneous, and if you want, it's completely predictable in the sense that everything is the same, the Simpsons diversity index is 1. That will correspond to our very ordered state. Now, the other limit case is given by the homogeneous scenario, where everyone has exactly the same probability, and in that case, the index for 1 over s will be what? It's easy to calculate because in this case, these will be just that expression, right? But that's code doesn't depend on k, so it's s times 1 over s squared, so it's 1 over s, and so that would be the result for this totally homogeneous and you think in the disordered state, all right? And this, if s is large, which happens very often, that would be the diversity index 1, right? So you have a whole range of values keeping our intuition in place that connect ordered and disordered limits, right? That's a good way of actually weighting to what extent the system is dominated by a single particular state, or instead it just distributes all over the place for every state. Of course, this is a very simple example. In a case, for example, in a gas, you might see a distribution of states which doesn't need to be homogeneous, right? But nevertheless, thinking in the terms we have defined, this is a good measure for what we pretend to measure. All right. This is for order and disorder. So in a way, we can start to think in terms of something that weights what is in this axis. But what about complexity? And that's very different. It's very different because complexity emerges from interactions. So we cannot think in complexity in terms of looking at states of elements and ignoring how the global properties emerge. All right? So we need something that actually defines who is interacting with whom, right? Somehow, because the correlations that emerge as a result of the interactions between individuals is what creates global organization, right? Remember when we talked about that, when we thought about models of interacting particles, and we mentioned the example of termite nests, right? Individuals interact, but it's a global structure resulting from that. You cannot explain anything from these single individuals. All right, so how can we define complexity? Somehow, we need to include interactions. For my example, and of course this is just a toy picture, right? Is like I have my dice. I've been talking about them as separated elements. All right. Let me put more states so that something different, right? And now what I want to show you is that what I need to put here is connect my elements somehow with other elements in a larger system, right? So the states of these elements are not any longer be independent with each other, right? And now we need to introduce some simple model that actually illustrates this idea. Okay, so the next step in order to put some order into this picture is to use a simple model, a very simple model that represents a way of seeing what are the mechanisms that are responsible for creating complexity out of interactions. As I was saying before, we define a measure of order, the Simpsons Index, but we need a measure of complexity, a simple measure of complexity. So let me use this model. This is called the majority model, It's connected with things that we have seen before, you will see, right? But includes a new element that sounds very trivial, but is responsible for creating high complexity in the system. What is the majority model? It's very simple. Imagine I have a lattice, right? A lattice of, I don't know, L by L sides. So this would be somehow defined as a collection of nodes, right? Imagine I take one particular node here, R, located at some place in the lattice, and I consider that the node has a given state, right? The state of my nodes is of R. Of course, R in this case will be coordinates in an integer lattice. S of R for me will be either 0 or 1. We have used that before when we analyze a model of brain activation. In a very simple way, we use that kind of Boolean description, as well as for genetic networks in our Boolean analysis of them. 0 and 1 here are not activity and inactivity, they're just two states. Okay? So that's my set of states that are available here, could be generalized in a number of ways. And around me, there's a collection of sites that can interact with me directly. So this here is what's called my neighborhood, right? I'm here at the center, and I have maybe just 4 neighbors, and I'm interacting with them. That's what's called the von Neumann neighborhood. Or I can have all of these, right? It's called the Moore neighborhood, right? The neighborhood for me in this model, right, will be everyone here. So who is around me and myself, okay? So in this particular case, and we used to write down this in this way, the size of the neighborhood, right, would be 9. Okay, it's 9 elements involved. Good. So what's the dynamics here? I haven't yet described anything. The dynamics is very simple. I start from a lattice where, for example, everyone is randomly scattered between zeros and ones, right? With no particular pattern. And now I do the following. That's the idea, and let's write down the mathematical expression for that. I take at random someone in the lattice, okay, and I look at the whole neighborhood, the 9 people there. If the majority is, for example, ones, I'm going to be a 1 myself. It doesn't matter if I was a 1 or a 0. With probability 1 minus p, meaning what? P is the probability that I do not follow the majority. In other words, the alternative is that I see that the majority is ones, but with probability p, I go into the other state, right? I don't follow them, right? Good. How can I define that in mathematical terms? The intuition is very clear, okay? And one way of putting this is the following. Suppose that h of r, what in physics we used to call the field, right, is just the average values, right, of the elements in all the neighborhood, right, the 9 elements. This is something that's going to be Q is in general, what's in my neighborhood will be 9 in this case, right? So the average will be between 0 and 1. And now the thing is, given this, if h is less than 1/2, right, which means that the majority is in state 0, okay, this majority 0, right, then S of R will be 0, okay, with probability 1 minus p, all right? And of course, it will not with probability P. P is a noise, it's a kind of a noise term, right? Whether or not I understand that the majority is this, right? And I made the right decision. And as you can imagine, we have the opposite case. If the field is larger than 1/2, the majority is ones, right? S of R would be 1 with probability 1 minus P2, right? Essentially, is that imagine that the probability, this probability P was 0. So I just obey the majority, right? So I just go into who is saying that, so everything is towards ones or towards zeros. And we have heard about that before. Remember symmetry breaking. Symmetry breaking, if you remember the examples we considered about technology and whether we can actually take one between two options, right? Depending on majority. It was more prone to move into one direction. The majority of people was using that. Now we introduce an element that seems trivial. The element is this, P, just a little noise. Doesn't seem to be terribly interesting, isn't it? It's not just symmetry breaking with noise, okay? It is not. And it's not in a very fundamental way. So this is something that I ask you to simulate. It's very easy. The rule I just described here is applied for randomly chosen elements. Every time step, you choose one element at random and apply this. And that's all, okay? Starting from any kind of initial condition. What can be observed here? And the result is very spectacular. Imagine that I do the following. This is P. This is going to be my parameter. I want the noise that is in the system. I'll take 1/2 as the maximum value. This is essentially a coin toss, right? I look at the neighborhood, but essentially I take a random decision. It could be 0, 1. I don't care, okay? Whereas here would be the case where I follow the majority. It's totally deterministic. And what's going to happen here? Well, I want to define something, right, that somehow captures the complexity of what's been observed, right? First of all, let me tell you what I'm going to observe, right? For P equals 0 is very easy. We are in the scenario that we already analyzed, the symmetry breaking problem. Here, imagine I start with half-half, random zeros and ones. For this case here, what is going to happen is that this time, this is, for example, the fraction of ones that I see in the system, right? If my system starts, this will be, the fraction of ones, normalized, okay? Starting from 1/2, zeros and ones. Sometimes my system is going to go to everyone once, because the majority rule is applied, right? It can take a while. If you simulate that, you could see that domains of zeros and domains of ones form, right, and compete, right? It's not trivial. It can happen the opposite, right, that the others win, right? But essentially it's symmetry breaking, right? That's all. So at the end of the process, and if you allow me to plot this as a sphere, at the end of the process, I either have everyone is zeros, right? Or everyone is ones. And that's all, okay? And you can actually think about what I just defined here and see that the mathematical theory, the differential equation, is what we saw in symmetry breaking. What happens here is also very easy to see. If essentially I ignore the information I receive from my neighborhood and I just take a random decision, it's going to be completely random, all right? Here I'll have disorder dominating my system. So essentially it's no structure at all. It's just zeros and ones scattered here, right? Here, if I look at the time series of the dynamics, right, And to make it clear, imagine that I start from an initial condition when, for example, the majority of elements are ones, right? 1. Here, they have a lot of elements in one state. It doesn't matter. I'm going to go fall down into 1/2. All right? I have fluctuations. I keep fluctuating, of course. I'm going to have this. And any other condition will go into that state. This is an attractor of the dynamics, right? So you've started with a collection of most of zeros. What's going to happen is this. It doesn't matter, right? Final state, highly disordered, right? No correlations, nothing interesting. What happens in the middle? And that starts to be interesting, because what can be in the middle between total homogeneity, remember what we saw with the Simpsons Index, and total disorder, right? And you can see easily that actually that could correspond with the 0 value for the Simpsons Index, that would correspond with the almost 1 value for the Simpsons Index, right? Order, disorder. And I just need something that measures complexity. But as I was saying, this has to be something that considers the interactions and the nature of the interactions, how rare interactions. Well, one way of doing that is to use a measure that's called, can be called, for example, the distance to independence, right? Meaning what? Imagine I take, and you can calculate that very easily with a simulation. I take one element, right? This is S of R, and someone in the neighborhood, right? This will be S R prima, right? And I do the following. For every pair that I can take in the system, I can make the following. See how often, on the one hand, how often I see an element having the 0 state or the 1 state, right? So I can have these probabilities, right? This for any element that I can look at the system. And on the other hand, I can look at the pairs, and here is where interactions come in. I can look at how often I observe there's a probability of having both in the state 0, 0, both in the state 1, but also the other probabilities. This is what's called for the pairwise interactions, right? The probabilities that weight how often I see 2 elements. And of course, considering them as connected elements, here come interactions, right? Very good. These are a normalized collection of probabilities. In other words, if I make the whole sum, it's just 4 terms, this is normalized, right? Good. Now, what is the measure of complexity that I can define? It's very simple. My measure of complexity is going to be this. I'll take for every pair of states, and it's going to be average all over the lattice, right? I'll take the probabilities of pairs minus, and you'll see why this is a consistent measure, right, of interaction. And I'm going to normalize this. It's not normalize, so make it positive all the time. Why I have chosen this? Well, because what I can see here is a comparison between what would be the prediction if the 2 elements will be completely independent, right? What is the probability of a state of 2 elements when they are just like 2 coins that I just tossed on the table, right? It's just the product because there's nothing there. But if there are interactions, and the interactions are actually defined by my rules, right? Then I have these joint probabilities. And the joint probability is going to be equal to this just in trivial cases. What trivial cases? And it's very easy to see. If I am here, okay, what I'm going to observe in my system at the stationary state? What I'm going to see is that all of the elements, or the vast majority of them, are going to be either 1s or 0s. So it's only one probability there. So meaning that for this p, for p equals 0, okay, I'll have, for example, these, if everything has gone into ones, and these, the rest are zeros, right? But that means that the only possibilities I'm going to observe essentially is that these are ones and these are ones, okay? But all the probabilities, this is going to be 1 and this is going to be 1, assuming that p is close to 0, right? If it's exactly 0 and it's dominated by ones, this is exact. And it's going to have, the only terms are 1 minus 1, 0. So complexity, as defined here, is in this place. Let's go into this part, right? When we have randomness. If we have randomness, by definition, we don't have to think much about that. The state, the probability of having a given state, a joint state, is just the product of probabilities, because there's no rule here. It's just the product. So for every single joint term, these and these are equal, right? It's independence. So complexity here, my complexity measure falls here to 0. So it's properly defined in this sense. What happened everywhere else, right? Well, two things you can do. And that's my proposal for you for doing the exercise. The first, let's simulate the system. Let's simulate for different values of p and measure complexity. And we observe is the following. Complexity is essentially flat here, rapidly rises somewhere, and then falls to 0 again. And has this precisely the shape that was mentioned before. There's actually a well-defined value of the noise. Remember, this is noise. It's nothing else that I have introduced. It's just some amount of uncertainty that is introduced in the model, but leads to a very sharp peak. What is in the peak? It's something quite amazing. If you look at the peak here, it's very difficult to plot, so you have to simulate that, right? Is that highly complex fractal structures emerge in space and time. So you will see very complex structures formed by islands of, for me, black is 1, for example, of ones, right? But these huge structures include islands of zeros that include islands of ones, and this is a highly dynamical structure. An enormous complexity emerges just from the tension between the fact that I try here to be as the surrounding is telling me, to be ordered as possible, and the disordered component, right? There's a tension here from this part, right, and this part, right? Trying to be ordered, trying to be disordered. If you look here now, what happened with these diagrams? If you look here, what happens is these are fractal objects. You can actually measure that properly. And if you look at the dynamics in time of ones and zeros, is not anymore like I just showed you before here, right? Go to 1/2, go to majority at all. And it's, again, is fractal. And actually, if you do that in a large scale simulation, if you take a zoom here, you would observe that what I just showed you in this scale repeats itself in smaller scales, right? So, complexity emerges as a tension between order and disorder. There are special values of the parameter space where models run, where I can see behavior. It's connected with phase transitions that we just mentioned in some point. And it reminds us from the very important lesson of complex systems. Extremely simple models that you can say this toy model is nothing really interesting going to happen here, are able to generate an extraordinary amount of complexity between order and chaos. And what remains for you also, you can use actually these measures and see how it works. You should find two things. One is that's one way of actually plotting my diagram there, but you could actually also measure the Simpsons Index as a measure of order and my complexity measure and see what kind of plot do you get, right? And think about its meaning. And my other challenge for you is what could be the mean field, mathematical minimal model that describes this phenomenon here, right? Where I have a new parameter p that I can introduce, and how far can you go from that, right? And that would be all. Thank you.